In this video, we're going to talk about how one neuron can communicate with another neuron, and this involves the propagation or the passing along of an action potential along the axon of a neuron. So here we can see two neurons, basically 1.5 neuron. If we look at the structures of a neuron, we first will notice these dendrites. These are appendages on the surface of a neuron. These are basically going to be responding to a stimulus. And on the dendrites, we'll see a very special channel called a mechanically gated sodium channel. So that when a dendrite is stimulated by something like touch, these mechanically gated sodium channels can open and sodium will flow into the cell. The sodium would flow into the larger structure of a neuron, which is called the soma or the body. After the body, we have the axon. In the axon, we have specialized channels called voltage-gated. And so these channels won't be opened by touch like the mechanically gated, but will instead be opened by action potentials. As we move on down the axon, the very end of the neuron ends in what's called an axon terminal. Here we'll see another type of channel called a voltage-gated calcium channel. So these channels are also opened by action potentials, but instead of allowing sodium to enter into the cell, it allows calcium. On the other neuron, on the surface, basically the soma, we can see that there is another type of channel called a ligand or chemically gated channel. This is also a sodium channel. So if we go back and look to recap, mechanically gated sodium channels are opened by touch. Voltage gated channels are opened by action potentials. And then the chemically gated channels will be opened by a neurotransmitter such as acetylcholine. Okay. Now let's look a little bit more closely about how an action potential is first created. And that's going to involve looking a little bit more closely at the extracellular fluid. So the extracellular fluid is any of the fluid outside of our neurons, and they are chock full of sodium ions. So every neuron is just surrounded by sodium ions. An action potential begins when a stimulus opens up these mechanically gated channels, allowing sodium ions now to enter into the cell. This will change the resting membrane potential of a cell from its usual negative 70 millivolts to something more positive. Let's go ahead and say 3 sodiums enter in. That might roughly change this to negative 67 millivolts. So for every positive sodium that comes in, that is going to make the membrane potential more positive, or you could say less negative. Now the important thing that we're looking at to create an action potential is to hit threshold. So I'll go ahead and write this out. Threshold in a typical neuron will be roughly negative 60 millivolts. This equates to a positive 10 millivolt charge change. So if you want to, we could just say this would be similar to maybe 10 sodium ions entering into the neuron. Once 10 sodium ions have entered into the neuron, we create an action potential. And it starts right here at what's called the trigger zone. The trigger zone is the area called the axon hillock, and this is the area between the soma and the axon. So if we hit threshold and create an action potential, that then has the power to open up this very first voltage-gated sodium channel. Okay, so the whole purpose of a mechanically gated channel is to allow for the neuron to be stimulated. In other words, to allow for sodium to enter into the cell, creating a change in charge of negative 60, and then creating an action potential. Okay, so now the action potential has been created, we're going to look next at the propagation, or how this action potential is passed along the axon towards the postsynaptic neuron. For that, we'll have to look more closely at the axon itself. I'm going to go ahead and draw an action potential here. So this action potential was once again created by the mechanically gated channels. It opens up this voltage-gated sodium channel, and that allows sodium from the extracellular fluid space to now enter into the cell. And likewise, once we get a positive 10 millivolt change, and you could, like I said, guesstimate that as to roughly 10 sodium ions entering the cell. This is not exactly accurate, but good enough for our analogy here. Once enough sodium has entered into the cell to reach threshold again, that creates another action potential. Okay, now that's the important part. An action potential opens these gates, allowing sodium in. It's the sodium that then creates the next action potential, which then has the effect of opening up the next gate. Once this action potential opens up the next gate, sodium is now allowed to travel into the cell through that next gate. Once enough sodium has influxed into the cell to change the overall charge to a positive 10, that then opens up our next channel. And this is what is called propagation of the action potential. So each opening of a channel creates another action potential, which then allows more sodium in, which opens up the next channel, creating another action potential. This action potential travels all the way down until we get to the end, or the axon terminal. The last action potential created has the effect of opening up a voltage-gated calcium channel. Okay, now calcium ions are also found in the extracellular fluid. So as soon as this channel is open, calcium is allowed to enter into the axon terminal, not the axon itself, and that is going to release a chemical called acetylcholine. All right, so we have two things at play here: an electrical activity due to an action potential traveling down, which ultimately has the effect of opening up calcium channels at the end of the axon terminal, and then that then releases acetylcholine. So let's go back and look at our original presynaptic and postsynaptic cells. This presynaptic cell is basically found as the talker. So the presynaptic cell is actually going to be the one that's going to secrete acetylcholine, and it's called presynaptic because the synapse here is the junction where these two neurons come together. So I kind of call this synapse the conversation place. So this is where the two actually communicate. And the postsynaptic cell, he will be our listener. All right, so the presynaptic cell secretes a chemical, and the postsynaptic cell is going to absorb that chemical and be affected by it. So if we look here, I'm going to go ahead and draw some acetylcholine. All right, let's go ahead and change this to white. So I'm going to draw some acetylcholine being released across this synapse, and when it binds to this chemically gated sodium channel, that's then going to allow more sodium to enter into the cell. So sodium is still in this extracellular fluid space surrounding our cells, and once the sodium is able to travel in, it's going to make the inside of the cell more positive. And once again, once we hit that 10 millivolt change, which could be roughly 10 sodium ions, that will then create another action potential. That action potential will then travel down and open up the next voltage-gated sodium channel along the axon. And that's how an action potential is propagated along from one axon to the next.